Hello, and welcome to a new lecture on Cantera. Today, we will be discussing how to calculate heating value of a fuel using Cantera, specifically the lower heating value. So the definition of a lower heating value, so there are two types of heating values. One is the lower heating value, and the second is the higher heating value. We will look at the lower heating value today. And higher heating value will be sort of an exercise for you to calculate, but that will come at a later stage. So the lower heating value of a fuel is the amount of heat released when unit amount of fuel at room temperature. So the fuel should be at room temperature when the calculation starts. Is completely burned and combustion products are cooled to room temperature. So the reactants as well as the products, both are at room temperature. However, the water that is produced in the combustion reaction, so most fuels have some amount of hydrogen in them, at least all hydrocarbons. So methane has 4 atoms of hydrogen. Similarly, ethane has 6 atoms of hydrogen. So all of these have some hydrogen, which produces water. Now, if the resulting water that is produced in combustion, if that is allowed to stay in the vapor phase and go away and vaporize, then the amount of heat liberated in the total reaction, or the amount of heat that we were able to use, is known as a lower heating value. And if all the water that has been produced, if that is condensed into liquid water, then the amount of heat that is obtained is known as a higher heating value, because now we have been able to gather the heat of vaporization, or the heat of condensation rather, from condensing the vapor phase of water to liquid phase of water. And so higher heating value is always larger in number than lower heating value. So taking hydrogen, for example, here on the screen, you see hydrogen combines with oxygen to produce water. Now, the lower heating value of hydrogen is 120 megajoules per kg, and the higher heating value is 141.7 megajoules per kg. So we will try to write a script in Cantera and calculate the lower heating value and see how close do we come. And the way this calculation is done is we take the enthalpy of the products, water in this case, and we subtract the enthalpy of reactants, hydrogen and oxygen in this case. And the resultant heat is the lower heat of vaporization, lower heating value that we will get. So let's jump into Cantera and start writing the script. So I'll bring forward, sorry, give me 1 second. I need to make a small change. Okay, so this is Spider again. Let's start with the usual, importing Cantera. So import Cantera as CT. Then let's again use GRI 3.0 as the data file, input data file for this case as well, because again, it has hydrogen and oxygen and water in its species. So gas equals CT dot solution GRI 30 dot YAML. Oh, sorry. Equals. Now let's set the temperature. So the temperature of the reactants and the products both has to be at room temperature. So that would be 25 degrees Celsius or 298.15 Kelvin. So let's go ahead and set the temperature and pressure of the gas. Gas dot TP equals 298.15, that's in Kelvin, and CT dot 1 atmosphere of pressure. All right, now, sorry. Okay. Now let's set the reactants. First, let's write the reaction. So we have the reaction on the presentation, but let's write it here as well. So let's put a pound sign to indicate that this is a comment. H2 plus 0.502 equals H2O. All right. So now let's first set up the reactants. So setting up the reactants, that would be hydrogen and oxygen. Okay, so gas dot set equivalence ratio of 1. Then we have hydrogen as fuel and oxygen as oxidizer. So what we've done here is we have combined, or we have produced a reactant mixture of hydrogen and oxygen in stoichiometric ratio, because by definition, for calculating the heating value of a fuel, the reaction has to be in stoichiometric proportion. It has to be complete combustion, so that the end products are only carbon dioxide and water, if it's a hydrocarbon. So we've done that here. Now, let's go ahead and find the enthalpy of these reactants. So these, the hydrogen and oxygen, this forms the reactant. So let's go ahead and find the enthalpy of the reactants. Finding enthalpy of reactants. Okay, so H react equals gas dot enthalpy mass. So if you remember, in the previous lecture, we've already in previous lectures we've already covered enthalpy mass, enthalpy mole. We will be working in mass units here because we want to calculate the heating value in terms of megajoules per kg. So since we have kg, we will be using mass units for enthalpy here as well. So this is the enthalpy of reactants. Now, let's go ahead and find how much fuel do we have in terms of mass in this mixture. So this mixture of hydrogen and oxygen, how much fuel, or how much hydrogen rather, do we have in terms of mass? So for doing that, let's again write a comment. Find amount of fuel in the mixture in mass, find the mass of it, let's say. Find mass of fuel in the mixture. So to do that, one very easy way is to, or let's say mass fraction. Let's start with mass fraction. And then we will see how to convert mass fraction into mass. So to calculate the mass fraction of the fuel in the mixture, what we need to do is, if we subtract the mass fraction of oxidizer from 1, because the total fraction has to be 1. And so if we subtract the mass fraction of oxidizer from 1, the remaining fraction will be the mass fraction of fuel. So here we will write fuel mass fraction is equal to 1 minus gas. In this case, oxidizer is O2, So O2 dot Y0. So in this gas mixture, we are looking for the mass fraction of oxygen, which is the oxidizer, and we're subtracting all of this mass fraction of oxidizer from 1. So this will be the fuel mass fraction. Now let's start this reaction and take it to equilibrium. So let's write initiating reaction. And we can do this by equilibrating the by taking the reaction to equilibrium, or let's say reacting the mixture. Okay, so now we calculate the equilibrium, and by calculating the equilibrium, we assume that the complete reaction has taken place. And now products and reactants are both in equilibrium. So there is no more reaction going on, or no more change in reactant or product concentrations. So we will say gas dot equilibrate. This time we will use TP. So what we're doing here is we are keeping temperature and pressure as constants for equilibrium reaction, for equilibrium calculations. Temperature is room temperature. So the products also have to be at room temperature. So the reactants have to be at room temperature as well as the products. So what we are doing here is we are saying that, okay, for the products as well, keep the temperature as 298.15 and the pressure at 1 atmosphere as well. And then let's calculate what happens. So we've calculated the equilibrium here. Now, so the products are formed. So let's go ahead and calculate the enthalpy of products. And let's write here, this is in joules per kg. All right, so now it will be finding the enthalpy of products in joules per kg. And that will again be H product equals gas dot enthalpy mass, right? So this will give the enthalpy of products. Now let's calculate the LHV. Calculating the lower heating value, which will be LHV is equal to products, enthalpy of product minus enthalpy of reactants. So H, and there is something that will happen here, and we'll see. We'll have to make some changes here later on. But first, let's write this line, and then we'll see what happens. H product minus H react divided by fuel mass frac. So what we've done here is now we are looking at unit mass of fuel being burned, because that is the definition of LHV. So by dividing this calculation by the mass fraction of fuel, we are calculating the LHV per unit kg of fuel. Right? So we've divided it by mass fraction. And if we want to, now this is all in joules per kg, right? So we have to go to megajoules per kg. So we again divide it by 1e6. So this will give the megajoules per kg. Let's write in megajoule per kg. Okay, so now let's print this out. Print LHV of fuel is equal to plus, let's convert this LHV into string. Megajoule per kg. Okay. All right. So now let's quickly save this and run it. So LHV. Okay. So see, it says LHV of fuel equals minus 119.95. So 119.95 megajoule per kg, but it has a minus sign here. If we go back to the presentation, which is here, it says it is 120 megajoules per kg. There's no minus sign, and it is 120 megajoules per kg. So what happened here was that we are supposed to put a negative sign because, and this is important. Let's go back one second. Sorry, just a little. Okay. So product minus reactant. That is what we've done here. Now, whenever combustion takes place, the products, the enthalpy of the products are always lower than the enthalpy of reactants. And that is why the spontaneous reaction takes place. So when we've subtracted this, what we've done is that we've, so the enthalpy of reactants is higher, the enthalpy of products is lower, and so we have a negative sign. So instead of that, we'll just put a negative sign here. And now let's run it again. And now you have 119.95 megajoules per kg, right? That's the LHV of fuel. So that's it. So this is very close to 120, like we've said in the presentation. So this is all on calculating the lower heating value. Now for the higher heating value, this is an exercise that I'll leave to you. And for calculating the higher heating value, what you will have to do is to find out the mass of water that was produced in this reaction. All right, and we've done these things before. So the way we have calculated, or we have found out the mass fraction of oxygen in the reactants, that is how, using some similar logic, you will have to calculate the mass of the water produced in the in the products. And once you know the amount of mass, the mass of water that was produced, you have to add the heat of vaporization or heat of condensation of that amount of water to the LHV to get the HHV, or the higher heating value. Now, I will also post the solution in the forum, or rather, you'll see in the description of the video, there will be a link to the solution for calculating HHV, but I will highly encourage you to do it yourselves first, and then take a look at the solution itself. So that was it for today, and next, I think we will start with a new module on chemical kinetics. So thank you. See you there.